I forgot, was synaptogenesis and synaptic degeneration. So you have neurodegeneration, neurons die, axonal degeneration, axons die, but then you have also at the end synapses. And synapses are more dynamic. So if you have a lot of synapses, more than 1000 per cell, per neuron. If the synapse is not used anymore, if you don't do something specific anymore, what for this synapse was created, then sometimes this synapse is going away. Or if you are more active, you are doing something, then you will get more synapses helping you to do that. So it's simplified explanation. And so synapses are going away and coming. There is such kind of constant synaptic regeneration. And it is relevant in context of neurodegenerative diseases, because in case of Alzheimer, in case of other diseases, you also have a less synapses. And it is not bad to increase your synaptogenesis. So there are no drugs, of course, available for that, but this is one strategy. So there are one of your old papers saying, for example, that if you are going to swim in very cold water, you know, in Nordic countries there is habit, snow everywhere, ice, and then there is in lakes or in ponds, there are holes in ice, and people are going, it's minus 10, minus 20 outside, they are going to swim for a few minutes. So it seems to be a strange thing to do, but the people like it, for example. I don't know why. So there is one old paper or several old papers saying that these people who are doing such kind of swimming in cold water, they will have some factors activated, expressed, that is increasing the synaptic generation. You have more synapses. And the same thing if you are old, you are passive, sitting in home and looking for TV, then you will lose your synapses more. If you are active, you are reading books, thinking, doing a lot of things, then you will keep your synapses longer and you will have more synapses, and your dementia is coming more slowly. So let's go then to neurodegenerative diseases. So this was the same slide we had before. So that the most frequent prevalent one is Alzheimer. It's approximately 50 million people living with dementia in the world at the moment, and from that maybe half have Alzheimer's diagnosis, or maybe two-thirds really have Alzheimer. So the numbers are lower in developing countries, in countries where population is young, but this is an average which gives this 50 millions. So Alzheimer's disease. So I have here about every disease. I'm trying to show you the symptoms. If I have some videos, I will show the videos explaining how patients are looking like, what is the main mechanism. I'm not explaining the mechanisms in very molecular way. And then I will spend a lot of time to explain what kind of drugs are currently used. So let's hope how the video will work.
In healthy people, all sensations, movements, Thoughts, memories, and feelings are the result of signals that pass through billions of nerve cells or neurons in the brain. Neurons constantly communicate with each other through electrical charges that travel down axons, causing the release of chemicals across tiny gaps to neighboring neurons. Other cells in the brain, such as astrocytes and microglia, clear away debris and help keep neurons healthy. In a person with Alzheimer's disease, the most basic form of dementia, toxic changes in the brain destroy this healthy balance. These changes may occur years, even decades, before the first signs of dementia. Researchers believe that this process involves two proteins, called beta amyloid and tau, which somehow become toxic to the brain. It appears that abnormal tau accumulates, eventually forming tangles inside neurons. And beta amyloid clumps into plaques, which slowly build up between neurons. As the level of amyloid reaches a tipping point, there is a rapid spread of tau throughout the brain. But tau and beta amyloid may not be the only factors involved in Alzheimer's. Other changes that affect the brain may also play a role over time. The vascular system may fail to deliver sufficient blood and nutrients to the brain. The brain may lack the glucose needed to power its activity. Chronic inflammation sets in as microglial cells fail to clear away debris, and astrocytes react to distressed microglia. Eventually, neurons lose their ability to communicate. As neurons die, the brain shrinks, beginning in the hippocampus, a part of the brain important to learning and memory. People may begin to experience memory loss, impaired decision-making, and language problems. As more neurons die throughout the brain, a person with Alzheimer's gradually loses the ability to think, remember, make decisions, and function independently. Achieving a deeper understanding of the molecular and cellular mechanisms and how they may interact is vital to the development of effective therapies.
Okay, so symptoms. So memory, functional changes, and behavioral changes. You have a three groups of symptoms. Cognitive changes, memory changes, means that you repeat yourself. You don't remember what you said a few minutes ago. You don't remember whatever you did few minutes ago. You don't know where are your car keys. This happens with me all the time. But it's not just the car key. Then you can't make decisions what to, how to say, to next. So you don't understand, you don't have a sense of time and space. You don't know where you are. You can't learn any more new things properly. And you do at the end, you don't remember or recognize your friends, and at the end you don't recognize your family members. So these are cognitive and memory changes. And then there are functional changes that you, because of these memory changes, you can't do anymore your everyday tasks. So you, of course, more complicated tasks go first, managing of finances, personal hygiene, dressing. So you can't move anymore fully normally. And so at the end this means that you will be in the bed. Somebody has to help you. And then also what is, sometimes you see that Alzheimer in films, in Western films, Alzheimer patients are, how to say, running away from the hospitals and so. So there are behavioral changes that patients may develop psychological and behavioral disturbances. They are behaving socially strangely. they have delusions, they are depressive, they are aggressive. They don't want to eat sometimes, or they eat too much, so the eating habits are not normal anymore. And actually these behavioral changes these are the main reasons why the patients anymore can't manage, can't cope at home, and they should move to the care facility. So, sorry. So these were the main symptoms. And so if you want to summarize, because they were very generic, then there are 10 symptoms listed exactly what are the risks that these are Alzheimer's symptoms. So I'm not reading them again from that slide, but you can see them summarized here. Okay. Then what is the reason for Alzheimer's disease? What is this initial trigger? It could be familiar, or it could be not familiar, sporadic. This means that in few cases we have the specific mutations. Few cases means approximately 5 to 10%. We have specific mutations in some genes which will lead to Alzheimer. It's listed here: presenilin 1, presenilin 2, APP, which is amyloid precursor protein. And the Mendelian genes means here that they are causative genes and they follow classic Mendelian inheritance patterns. And then you have a number of risk genes where you don't get Alzheimer, but your risk to get it is increasing considerably. And the most frequent one, or most high risk one, is this ApoE4, which is most frequent and most serious risk, high risk also. What usually happens is that if you have a mutation in these causal genes, then the Alzheimer is usually coming early. It's early onset familial Alzheimer disease. And if you have such kind of risk gene, for example this ApoE, then it increases your risk for late onset Alzheimer. So maybe you don't get it, it just risk is going up. So early versus late. By definition, early is if it comes before age 65. Sometimes it's already as early as at 30, 40. And then, as I said, it's associated very frequently with these mutations, but sometimes not. Then late onset is when you get it after age 65. And this is most common. It is mostly sporadic. It is mostly not inherited. And it is the majority. And as you can see from the table, the risk, or not a risk, but prevalence is going significantly up with age. From 65 to 69, it's relatively small. But if you go to 90 plus, then it's already very high, 25 per 100. So the age is main determinant of Alzheimer's disease. Then it's not so easy to find out whether somebody has Alzheimer or not. If I will forget my car keys and I have few symptoms, then this doesn't mean that I have Alzheimer. And all these so-called symptoms we had before, they are very subjective. So how, in clinical settings, how to diagnose Alzheimer's disease? So the first is just the general assessment. So cognitive evaluation, tests. Then the medical history check. Sometimes you will see if the patient was very fit a year ago and now everything has happened very quickly, then the probability that something happens, there is Alzheimer, is higher. If the person has been like that, strange but like that, already 20 years, then it's less likely that there is Alzheimer. And then there is also the neuropsychiatric and behavioral assessment, how the mood, personality changes has been affected during last period. So the functional tests. This is just to see how functional the person is. I mean, can the person do everyday tasks? Then the laboratory tests. Unfortunately, we don't have a proper laboratory test for Alzheimer. So here the laboratory tests are actually not to diagnose Alzheimer, but to exclude other possible causes for dementia. Not all problems or dementia is because of Alzheimer. Sometimes it's related to something which is reversible. Then what is less likely, what will be done, is the imaging, MRI, to see the brain atrophy. But you see, this is at the beginning, it's not visible, the brain atrophy. It's visible only at the end if everything is quite strongly affected. And then biomarkers. So this is more tricky because actually in clinics we don't have proper biomarkers. We have some biomarkers related to how much we have beta amyloid versions or variants in the blood, and so how much tau, how much phosphorylated tau, but they are not really very much used. Some tests are commercially available in States, but they are expensive, they are not so precise, and also because of the almost lack of the therapeutic approach, they are not so helpful. So the main thing at the beginning, how to diagnose early stage Alzheimer, is unfortunately only this evaluation, clinical assessment. Then dementia. Is dementia same as Alzheimer's disease? So it's not, but quite frequently dementia is not, it's used instead of the Alzheimer's disease. So Alzheimer's is specific disease and the most common cause of dementia, while dementia is the syndrome, general term for cognitive decline. And it's mostly Alzheimer, but not always. But since it's difficult to diagnose the early stage Alzheimer, people or doctors can diagnose dementia. They can't diagnose early stage Alzheimer's so easily. Because of that, dementia is sometimes used as a term instead of Alzheimer's disease. So the reasons for dementia could be also related to stroke, Parkinson infections, or trauma. Symptoms are very similar. Diagnosis is also very similar. If you have 55 million dementia patients worldwide, then maybe 50, 60, 70% is Alzheimer. Then what kind of scales doctors use to quantify how strong is dementia or Alzheimer? So there is such kind of most common and simple is mini mental state examination, which is used, but in specialized clinics and centers they prefer the clinical dementia rating CDR, which is gold standard. So it has rating from 0 to 3, and then according to that, what is the damage to memory and so on, orientation, judgment problems, and so all these things which could be assessed, how strongly they are affected. So according to that, it will be decided what is this dementia rating. So as you can see another graph here, from this dementia rating, it depends how well the patient could manage. So that if the dementia rating is 0.5, it's a very mild dementia, then the patient needs some minor help. But from the dementia rating 1, CDR 1, the life becomes more complicated, so no hope to thrive anymore. CDR 2 full-time supervision, and CDR 3 means almost amazing bed. Patient in the bed only. So this is what could be used clinically to say whether the dementia here is mild, severe, moderate. Then there is another very popular ranking or staging system, Prague staging system. This is based on neuropathology. So you really can see that if you have a patient coming in, you can see it only after the patient is already gone and you will do the pathological examination. So that Prague staging at the beginning means that there is tau already coming and there is, how to say, damage in hippocampus. Everything starts from hippocampus. Prague 1, 2, it takes quite a long time. Then the damage goes to the cortex, echorineal cortex and so on, Prague 3, 4, and then the damage is going to be stronger, Prague 5, 6. So all the cortex area is affected. So this Prague staging says what was the, how to say, the stage of Alzheimer development at that moment. Okay, so what then really happens in the brain? So it's the Alzheimer is the neuronal death, loss of axons, loss of synapses. As it was told, it starts from hippocampus, entorhinal cortex, and then it goes on to everywhere. You can see that at the beginning, but if it is already moderate, degeneration is making your brain smaller, then it's detectable using imaging. What happens at the level of the cell? So two types of changes that are visible. One is the amyloid plaques, means the beta amyloid is forming extracellular deposits that are insoluble, and it's not just beta amyloid there, but also something else, some other rubbish, You have a big amyloid plaques. And then you have neurofibrillary tangles, intracellular aggregates of hyperphosphorylated tau protein. So these are main things that could be seen at the cellular level. So there are a lot of different speculations and hypotheses actually why these things happen and what happens after you have this initial beta amyloid or tau accumulation. So it's you can see this amyloid and tau are mentioned here, but then there are a lot of other things. So there is inflammation or inflammatory hypothesis. So if you have a lot of rubbish inside of cell and outside of cell, then the likelihood that the inflammation will start is higher. So you may have more likely inflammation. Or another explanation is that there is something else that will also induce inflammation and that will kill your cells. Then there is microbiota, gut-brain axis hypothesis. It says that somehow your microbiota, what you have, is affecting the brain. It was very popular some time ago, maybe less now. Then there is autophagy hypothesis. Autophagy is to remove the rubbish. So if autophagy is not anymore properly working and it's not removing the rubbish, then the rubbish, in this case tau and beta amyloid, they will start to accumulate. Then there is mitochondrial Ross hypothesis. Is that mitochondria are not happy, they are damaged, they are starting to produce a lot of free radicals, and the free radicals are affecting the cells. Then there is cholinergic hypothesis, saying that you have less cholinergic signaling, and this is affecting the system. And there is glutamate excitotoxicity hypothesis, which is saying that you have too much glutamate, you have too much excitation. Too much excitation leads to excitotoxicity, cells will die. So you have altogether here 8 possible factors listed. Some are primary, amyloid, tau. Some are most likely secondary, cholinergic hypothesis, excitotoxicity hypothesis. But we really don't know example for the autophagy. Is it primary or secondary? How much it is contributing? But 2 main hypotheses are related with beta amyloid and tau. There are Baptists and Taoists, suggesting, one group is suggesting that it's beta amyloid that is bad, another group is suggesting that the tau protein is bad, or most likely both are bad. Let's start from the beta amyloid. So beta amyloid precursor protein, APP, is located in neuronal cell membrane. It's not fully clear what it is doing there, and it's not relevant in this context at all. It's mostly outside of the cell, or most of it is outside of the cell. And like all other extracellular or intracellular proteins, these proteins needs to be broken down to maintain if they are becoming old, and there should be system to avoid their accumulation. And then if they are broken down, you will get new fresh proteins coming from ribosomes. So it's how to say, unclear what protein is doing, but it's clear what happens later. So if it's necessary to cleave this protein, to send it to rubbish, then it's first cut by beta secretase, and then what remains will be cut by gamma secretase. So this gamma secretase is actually not one protein, it's the complex of several proteins, and presenilins are part of this complex. And then, if everything goes well, then these fragments after this cutting will be just removed and destroyed by the cell. But then one of these fragments is more, so to say, sticky than other and can't be demolished further. It starts to form the fibers outside of the cells, and this will lead to amyloid plaque formation. I have one more detailed explanation about that in this video also.
APP processing and plaque formation. Excess amyloid beta peptide is believed to be a main contributor to the dysfunction and degeneration of neurons that occurs in Alzheimer's disease. A beta is a 38 to 43 amino acid peptide that is derived from the beta amyloid precursor protein, APP. APP to a larger evolutionarily conserved APP superfamily protein family that includes the APP itself and amyloid precursor like protein 1 and 2 in mammals. All of them are single-pass transmembrane proteins with large extracellular N-terminal and a shorter cytoplasmic C-terminal. The APP superfamily shares several conserved domains. However, only APP generates an amyloidogenic fragment owing to the unique A-beta domain in sequence divergence. Though expressed in many tissues, APP is concentrated in the synapses of neurons in the central nerve system. APP can be sequentially two different ways by different sets of enzymes. An amyloidogenic pathway leads to amyloid plaque formation, while a canonical pathway does not. In general, almost 90% of APP undergoes the non-amyloidogenic canonical pathway, and 10% the amyloidogenic pathway. However, the ratio can be altered by genetic mutations, environmental factors, and the age of the individual. Cleavage products of APP from both pathways play diverse roles that are important in neural development and function. The non-amyloidogenic pathway involves cleavage of APP by alpha secretase to generate two fragments. An 83 amino acid C-terminal fragment that remains in the membrane, and an N-terminal ectodomain SAPP alpha that is released into the extracellular medium. 3 enzymes have been identified with alpha secretase activity: ADAM9, 10 and 171. Importantly, cleavage of APP by alpha secretase occurs within the A-beta domain and consequently prohibits A-beta peptide production. Of note, the C83 membrane fragment can be subsequently cleaved by gamma secretase to produce a short fragment called P3 peptide and a C-terminal fragment. To date, the P3 peptide is believed to be pathologically irrelevant. The amyloidogenic pathway leads to neurotoxic A-beta generation. BACE1, the major beta secretase in the brain, mediates the first proteolysis step, which releases a large N-terminal ectodomain, SAPP beta, into the extracellular medium. A 99 amino acid C-terminal fragment remains in the membrane. The newly exposed C99 N-terminus corresponds to the first amino acid of A-beta, Successive cleavage of this fragment between residues 38 and 43 by gamma secretus releases the A-beta peptide. The genic pathway occurs in the endocytic pathway, as beta secretus mediates the first proteolysis step in mature endosomes. The successive cleavage of C99 leads to the generation of A-beta peptides, which are secreted outside the cell. Monomeric and oligomeric forms of A-beta overwhelm the brain's capacity for clearance and degradation and form extracellular plaques, causing neurotoxicity through several mechanisms including microglial infiltration, oxidative stress, and synaptic damage. Most of the peptides are 40 residues in length, A-beta 40, with a small percentage containing 42 residues, A-beta 42. A-beta 42 is considered the more neurotoxic form, because the extra 2 amino acids provide a greater tendency to misfold and subsequently aggregate. Elevated plasma levels of A-beta 42 have been correlated with Alzheimer's disease. For more information, please visit Creative Diagnostics.
Okay, so what you remember?
APP process.
What you remember from that is that you have different peptides. Some peptides are more toxic than others, and forming the fibrils, and then also some of these peptides will later go to the blood, so that you can theoretically measure these peptides in the blood, and if you have there in the blood more bad peptide compared with not so bad peptide, then it's in some sense biomarker. So the kits available commercially, they are measuring the ratio of these bad and not so bad beta amyloid. So another hypothesis, tau hypothesis. Tau is microtubule associated protein. It's just part of that railway through which all the motor proteins are running with cargo. If this tau becomes excessively phosphorylated, then it detaches from the microtubules and start to form these neurofibrillatory tangles. So these neurofibrillatory tangles, they are themselves bad. You are having some aggregates in narrow axons, and they are maybe blocking the movement there. But also another thing is that if tau goes out from the microtubules, then this railway becomes, how to say, not so good. The traffic, axonal transport becomes more slow. So these two things together, or one thing more than another, accumulation and inhibition of axonal transport, is the basis of this tau hypothesis. So this is all about the mechanisms. So it's now pharmacology, which is more, how to say, complicated and also less interesting, but much more relevant. So what doctors will prescribe if the people have Alzheimer or dementia? So here you have the UK guidelines from British medical journals that they have two kinds of drugs. These anticholinesterases, free drugs, donepezil, galantamine, rivastigmine, and memantine. So if patient will get the diagnosis mild dementia, then the recommended start is monotherapy with anticholinesterase. If the patient will get the diagnosis of severe dementia, then it's recommended to start with memantine. So both together is also okay option, but this at the beginning monotherapy is recommended. why these compounds. So if you remember this circle from previous slides, then there was this cholinergic hypothesis. So that quite early the Alzheimer brain is losing cholinergic neurons in the forebrain, and there is no cholinergic activation anymore. So the logic is very simple. We have this pathway activated. How to get this activated? We inhibit the breakdown enzymes who are breaking down acetylcholine. So we have more signal. So free compounds available. They inhibit, as I told, acetylcholinesterase. You have more of it in synapse. They will activate postsynaptic nerve terminals more actively. The difference why these three compounds, there is difference. One is selective acetylcholinesterase inhibitor, another is combined. It inhibits acetylcholinesterase and butyrylcholinesterase. Butyrylcholinesterase is coming from astrocytosine, so you will theoretically get stronger inhibition. And then there is galantamine, which is positive allosteric modulator of the acetylcholine receptors. So receptor response is stronger. So all these three are used. They are already relatively old. First came 96, another 2000. And there is no really clinical difference between them, with exception of the half-life. So if you are developing drug, for example, then it doesn't make sense to develop drug that you will have to take, or pill that you have to take 10 times per day. So the best is 1 times per day. If it's not achievable, then 2 is also okay. I mean, if it's acute disease, 1 week, then you can do whatever antibiotics. But if it's, how to say, lifetime disease, then the pill should be, how to say, optimized. So, because of the different half times, since galantamine 7 hours, rivastigmine 1.5, donepezil 70, you have to take them once or twice per day. So they are all quite similar. They are all quite well tolerated, and the symptoms they have are not so important. Loss of appetite, nausea, vomiting, diarrhea. So quite okay to take them. Then another one was memantine. So you remember excitotoxicity hypothesis. Means that we have too much excitation, too much glutamate. So because of that hypothesis, it makes sense to inhibit this excitation. And memantine is the NMD receptor, it's glutamate receptor antagonist. So you inhibit glutamate receptor, you will get less excitation, and it's good. So its half-life is long, once per day, well tolerated, side effects acceptable. So both are working, but they are symptomatic. Means that they will improve a little bit your symptoms, but your disease is developing further and effect is small. So if we will take just 2 clinical studies to explain that better. So here is the clinical study with memantine. and it was the moderate to severe Alzheimer's disease alone or with cholinesterase inhibitor. So you see in placebo, here we have weeks and here we have a behavioral scale. This behavioral scale was becoming worse from 0 to 0.8 in placebo patients, and it was twice less in patients who took memantine. So the behavioral scale or behavioral symptoms, they become worse, but not so quickly as in placebo group. Or another clinical study with if I'm correct, then with patients who have a mild Alzheimer's disease. So here it was memantine, one group plus acetylcholinesterase inhibitor, and here we have this cholinesterase inhibitor, acetylcholinesterase inhibitor alone. So you see that memantine made the situation even, my mistake. So that the memantine together with this another compound was beneficial, so the result was better. So I'm not explaining these in very great details, these graphs, but actually these graphs and these studies are the basis why they have suggestion that in case of mild dementia Alzheimer, you should start with one drug. In case of severe, you should start with another drug. And if it's severe, then you can have both drugs. So that this is not coming, these rules are not coming from nothing, but they all come from such kind of clinical studies. And that's it. So we have two drugs that could be relatively routinely used. Then ginkgo biloba, I don't know what is the, how well it is known in India. It's growing here, and it has another name. But it is in Western countries, it's very popular. Ginkgo biloba extract is very popular, and people are buying a lot from the pharmacies, and they are thinking that it is having preventive value. It is preventing dementia and Alzheimer's disease, or they are not thinking so seriously. They are saying that it's good for memory. But the general idea is that they hope dementia will not come. So the statistics shows that quite many people are buying it and eating it. But then if you take the proper studies, so this Lancet studies shows here that it doesn't really matter whether you take it or not. So one group is eating ginkgo biloba, another not. There is really no difference here. So the dementia or Alzheimer progresses anyway absolutely similarly. So they made conclusion that it says that in general population it's not preventive, but always there is possibility that there is some small subgroup of Alzheimer patients where it is helping. And another conclusion they made that it is very safe, it is cheap, and if people will eat it, it's not harming anyway. So it's not useful, but it's not harming, so nobody cares. But there are no really anything for prevention. Then what is the new development? New development is antibodies. So these drugs before were symptomatic, but antibodies are disease modifying. This means that they are a little bit at least suppressing down the development progression of disease. Antibodies. So the first antibody that came was aducanumab. So it was 2020, I think. Sorry? Okay, that's good. And the idea was that it removes the beta amyloid from the blood. Antibody is not going to the brain, but it's removing beta amyloid from the blood. And if you have less this bad beta amyloid in the blood, then it's more probable that it will go out from the brain. And you have less in the brain, and it's good. So the first studies in mice were very good. And when it first was accessed by FDA, it was 2020, then FDA decided that the effect is so minimal in patients that they don't recommend it. But then it was first in the class drug, and public was suppressing. So then the FDA changed the decision 2021 and accepted it. But despite of that, it is not anymore in the market. 2 reasons: it was not very useful, and now we have another antibody. This another antibody is this lecanemab. So this is monoclonal antibody similarly, and it targets also this amyloid beta. And it is also, because of that, you have less in the blood, you will have less in the brain. I will not show you this clinical trial data here, but it was more or less effective, but not so effective. I mean, it was not 100% effective. Okay, I will not get it open. If I remember correctly, it was 1/3. I'm not completely sure. It's expensive annual treatment, as you can see, $26,000 USD at that moment when I made that slide, at least. Why this antibody is better, this lecanemab, than this first antibody? So one explanation is that it is recognizing different kind of beta amyloid. So when we take this aducanumab, then it was interacting with beta amyloid in fibrils, while this lecanemab binds to smaller protofibrils. And people are thinking that these protofibrils are more relevant in this context, so that they are more toxic and it's better to block it at that level. Difficult to tell whether it is so, but this is one of the explanations. So it seems good. It's not reversing the disease fully, but it's helping a little bit. It's expensive, but not so terribly expensive. So why not? But there are side effects. So side effects are called main side effects amyloid-related imaging abnormalities, ARIA. So this ARIA is quite often asymptomatic, but in some cases it is more dangerous. It's inflammation places in brain, or small bleeding areas in brain. Why exactly this happens, no idea, but the probability that this happens is 20 to 40%. So this is serious problem, and now people are trying to find a way how to predict which patients will get this ARIA and which patients will not. So I have about that little bit more in one of the lectures coming later. So Alzheimer, that was Alzheimer. What are your questions? Yes. At least this is one of the explanations, yes. Because the probability that the beta amyloid will leave from brain to blood is higher if you have less in the blood. I don't know actually. But I'm not sure whether people have measured that, but if the clinical studies show that Alzheimer is developing more slowly, then actually you can't invent other explanations. If you have less beta amyloid in the brain, why you have less? Most likely you can't change the formation of beta amyloid in brain with an antibody in blood. So only logical explanation is that it goes out from the brain. I don't know too much about that, but I can't invent other reasons. Plaques are no. I mean, plaques are not going to the blood; they remains in brain. So the tau fibrils are inside of the cells, and the plaques are outside of the cells, between the cells in brain, and they are not. Plaques are not going away, but this how to say, maybe small fibrils and soluble one is going away.
Does that mean that the blood-brain barrier is getting weaker and that's why the plaques are...
That's a good question. So it's difficult to explain. So if you think about the blood-brain barrier, then it has holes. They are not exactly holes, but so if this is the brain, there is barrier, and I think the synuclein amyloid can't very easily pass the barrier. But then you have also blood vessels coming in, and in these contact points are a little bit leaky. So theoretically, there is such kind of washing happening. It's like a brain lymph system which washes the brain, and this means that from here you have some movement in or movement out from these holes where blood vessels are crossing the blood-brain barrier. Again, I'm not specialist in the field, but it doesn't mean that everything should pass the blood-brain barrier. You can have such kind of holes. So I don't know, was it helpful? Maybe a little bit. Yes? Okay, I will.
Just a normal question. So, the main idea of Alzheimer's was that yes, there is the trash collecting system has gone awry, and we just have the systemic inflammation in attachment is causing. Neurons to not be able to talk to each other, and then progressively they are degenerating. So, sir, comparing and contrasting this to, say, for example, somebody who has epilepsy, and then in a lot of cases, like grand mal seizures, they do have lobotomies of certain lobes. Now, a lot of those people are there. I think it's more severe because a chunk of the brain is pretty much taken out. But the rehabilitation processes that they are subjected to can be or are those already used for Alzheimer's patients?
What exactly to use in Alzheimer's?
So rehabilitation. So for a lot of people with lobotomies, they ask them to do certain exercises, certain motor rehabilitations, a certain.
Okay, I got it. Yeah.
So do we do that for Alzheimer's?
If you do such kind of rehabilitation or whatever, then you cannot change the cause of the disease. Anyway, the beta amyloid is aggregating and everything happens. But what you can do is you can little bit improve the symptoms. If you are active, you are doing whatever rehabilitations, then the symptoms are not worsening so quickly. So it helps to improve the symptoms, but it's not, in my opinion, it's not affecting the disease progression.
So it can be an addition to whatever pharmacological.
Yes, yes. It's I think in these two compounds or drug groups used as a symptomatic treatment, they are okay. You can add to this physical activity, which is always good, not just for Alzheimer patients, but for all old patients, old dementia patients. So then I have a question to you that at the moment there is no real treatment. There is this antibody. Antibody is efficient, partly. It's expensive and it should be started quite early. Is it making sense to develop new diagnostic kits or tools for disease which has no real treatment? No disease modifying treatment.
Somehow we can target slow progression. If we diagnose the disease early, we can difference of drugs
Yes.
and try some treatment so that the progression of the disease is a bit slow, even if there is
Yes.
no specific drug or anything available. Like some, as she said, some rehabilitation vectors or some other things.
So, but if you don't have, well, let's think, you don't have a drug, and you apply for a grant where aim is to develop diagnostic for that disease. What they say, quite frequently they are saying that it is not helpful. If people will know early that they have some kind of disease which could be treated, how it helps? Not really. But it really helps when you have some kind of treatment. So before this antibody came, people were thinking that there is really no need for Alzheimer test, because if you know that you have it, nothing could be changed. Now we have antibody and maybe better antibodies coming. Now it makes sense to have a test to get as early as possible the diagnosis, because these behavioral scales or whatever, cognitive capacity, they are not very precise at the beginning. So if you are very clever person and you have very good IQ, then it takes long time before this questionnaire will catch you. You have to lose a lot of your intellectual capacity to get your diagnosis, and then it's already quite late maybe. But if you have a blood test which is saying that, this beta amyloid bad and good beta amyloid ratio is changed, you can get it faster. And theoretically, if there is drug, antibody, you can get your treatment faster. So, but 5 years ago, I remember when evaluating applications, then the agency said that we don't want tests for the diseases which do not have proper drugs. Good.
So now we have a next disease, Parkinson. So Parkinson disease got its name after the English physician James Parkinson, who published an essay of the shaking palsy. And this is the first time it was documented. So I have one video again showing the patients. Let's see, will it come? Yes. So this is the, how to say, mild Parkinsonism, early stage. So what is different? Different is movement, so the steps are somewhat shorter, and then the hands are moving. So let's slightly strangely, and especially one hand, so there is a possibility that one hand is moving more than another less. So if you remember from the news, then when this war in Ukraine started, then they had a picture of the Russian President Putin who was keeping one hand always like that and another was moving, and they were saying that, Parkinsonism. But another option was, explanation in newspaper was that because he was a previous security police person, that this was trained to keep it close to the arm or gun. Sorry, no. So then it goes on the advanced stage, and in advanced stage you will see this movement is becoming more complicated. Steps are shorter. So this is the main symptom. These are the main symptoms, that the limbs have some kind of tremor, steps are short, body is very rigid,
and the head is usually like that.
And this is one thing, motor symptoms. And then there are secondary symptoms, non-motor symptoms, depression, speech disturbances, and many other symptoms, from salivation to constipation. But what is very different from Alzheimer, that this is just at the beginning motor symptoms. So if Alzheimer patients will first lose the memory, and because of that they are becoming socially inactive, then Parkinson disease patients, they don't have at the beginning any intellectual problems. They are still remaining active. So therefore you have many famous people here So there are pictures of Muhammad Ali, Michael G. Fox, previous Pope, and Yasser Arafat, who actually had a Parkinson disease and who were still, how to say, still active after that. And for example, Michael G. Fox, who got the Parkinson quite long time ago, what he did, he established the Parkinson Disease Fox Foundation. And this foundation is funding quite well the Parkinson research at the moment. Similarly to Alzheimer, there are a lot of genes which are causative, which means that if they are mutated, you will have, or there is very high probability to have the Parkinsonism. And then you have some intermediate risk genes, and then most of the patients do not have clearly defined mutations. So in most of the cases it's sporadic again. If you take the prevalence in different countries and in different age groups, then in some countries you have more, in some countries less. But what is clear that it is coming after 60s. And then the prevalence goes up. It's quite much increased at 80s and 90s. Main pathological finding is the degeneration of dopaminergic neurons in striatum. So you lose these tyrosine hydroxylase positive dark neurons, and if you do the PET scan, then you don't have the dopamine anymore. So this is normal coming from visualized from striatum, and then in case of Parkinson's disease, there is almost no dopamine left. So if patients will lose maybe approximately half from their dopamine, then the symptoms will come. So the PET scan actually is very sensitive. It shows already something at very early stage. At cellular levels, the hallmark is the Lewy bodies. They are not always present. In some cases it's Lewy body negative, but in most cases they are present. And they are cytoplasmic inclusions of alpha-synuclein together with other stuff, ubiquitin, neurofilaments, whatever proteins. So Lewy bodies containing alpha-synuclein in striatum in substantia nigra. Why this happens? And what exactly happens? So the core pathological mechanism is the alpha-synuclein aggregation. These alpha-synuclein aggregations are toxic, and they are spreading also a little bit like prions. Okay, I will explain it slightly later. So they could spread from one place to another. There is hypothesis also that it starts from one place, from gut enteral neurons maybe, and then it's moving to brains, then brain, and then so I don't know too much about that, but so this spread, this alpha-synuclein is spreading. So then another thing what happens is that there is dysfunction of lysosomal, endolysosomal system. So autophagy is inhibited. Autophagy is not removing anymore this misfolded alpha-synuclein. Or there is this BA mutations that affect also the lysosomal systems and vesicle trafficking. And then there is mitochondrial function. This well-described PINK1 Parkin pathway, which is related to mitophagy. It's mitochondrial removal by autophagy. There is less ATP production if mitochondria are not happy. Yeah, and mitochondria are signaling to apoptotic pathway also. So there is maybe more neuronal loss and apoptosis. So we can't tell that alpha-synuclein is only one thing. There are three different possibilities. If you take this pink and Parkin dependent mitophagy, then we really don't have alpha-synuclein aggregates so much. We don't have Lewy bodies. So there are different mechanisms. Alpha-synuclein aggregation is the major, most important, but you can have Parkinson's disease also without it. So how this alpha-synuclein is exactly toxic? So actually nobody knows that. There are many speculations and good works and bad works, and I don't know how it works. This is the last paper, just maybe a month old, where they showed that alpha-synuclein oligomer in plasma membrane will form such kind of unspecific pore, and that this pore, that several molecules, whatever, could cross this pore from intracellular space to cell. So I do not know whether this is the case or not, but this is just to illustrate that it's not exactly clear how alpha-synuclein accumulations are toxic. And since I don't know that, I don't speculate further. Then pink and Parkin pathway. This is what we are studying also in our lab. And this is now very well established and it's clear. Almost clear. So that if mitochondria damages, mitochondria is damaged, it depolarizes, then the kinase, PINK1 kinase, will accumulate to outer membrane. If it's in the outer membrane, then it will attract another enzyme, ubiquitin ligase Parkin, to mitochondria. This ubiquitin ligase is phosphorylated by PINK and it becomes active, and it will start to ubiquitinate other proteins in mitochondrial outer membrane. And these ubiquitinated other proteins, they will attract in autophagy adapters. So it's optineurin and others are listed there. And autophagy adapters will help in autophagosome formation, and this bad mitochondrion will be surrounded by autophagosome, and autophagosome will fuse to lysosome, and it's gone from the cell. So it's the quality control, mitochondrial quality control. That happens also in neurons. Now if there is PINK1 mutation or Parkin mutation which blocks this process, then this is not happening. This bad mitochondria remain in cell, and the cell will have problems. These bad mitochondria are producing maybe a lot of free radicals. They don't produce much energy. So cell is not happy, cell will die. And for some reason, the dopaminergic neurons are most sensitive. Not so clear why they are more sensitive. One speculation is that they are more sensitive to ROS than other neurons, and because of that they will die first. It's a good explanation. Is it correct or not? I don't know. And so these neurons are dying and we will get the Parkinson symptoms. And we don't have alpha-synuclein aggregation. So it's also possible that the mechanisms are different. Pink and Parkin pathways inducing Parkinson one way and alpha-synuclein another way. Both are killing same type of cells. So drugs. Now it's much more complicated than with Alzheimer. So there is such kind of golden standard drug, levodopa. It came from 60s, and first as an infusion, then as a pill or tablet. And it was really through breakthrough then. Then came amantadine, then dopamine agonists in 70s, then MAO-B compt inhibitors, and after that, after 90s, there was long time really nothing, and now I think we got 5 years ago we got adenosine A2 receptor antagonist. So this is what is available, but if you just showing you the pipeline is huge in clinical trials. So again, I'm showing you the treatment scheme. So in case of Parkinson, there are maybe two independent treatment schemes. One is to treat non-motor symptoms, as I told, salivation, sleep disturbances, hypotension, hallucination, whatever. And then another is to treat motor symptoms. So these levodopas, etc., they are to treat the motor symptoms. What is the point? So the point is very easy, that if you don't have dopaminergic neurons, or you don't have them enough, then you give more dopamine. Dopaminergic neurons produce dopamine, you are just giving dopamine. The dopamine itself is not going to brain because of brain-blood barrier. So therefore what is used is this levodopa, which is precursor of dopamine. So you can see it here and here. So if this levodopa goes to brain, then this dopa, the carboxylase, converts it to dopamine, and there is more dopamine available. So the neurons are dying anyway, so it's how to say, in some kind of like symptomatic treatment. It's not really keeping the dopaminergic neurons alive. But what is the problem? Problem is that it's at the beginning it's very good drug, but after some time, half of the patients after 5 years, they will have a very serious side effect. Dyskinesias, wearing off phenomena, means that they have a lot of involuntary movement coming, which is very complicated. I will show the video about that. Then they have these on and off fluctuations, which means that they have this hyperactivity, and then at some point they are completely off, not moving at all. So they are going from one extreme to another extreme. So this is problem that is long-term motor side effects. So it's more problem when the treatment is very long. If the young patients are coming in, they respond very well. After 5 years, these side effects will start. So there is one extreme case. So this is extreme case, and there is apomorphine injections to calm everything down. So if you have such kind of side effects, then the question is maybe to be completely off, which might be better than to have such kind of dyskinesias. So, oops. Yes, if you like, then we can have.
Break of 10 minutes for tea. Then we can start again.
Okay.
So tea is outside. Everyone is joined, and just be quick. We will continue with the session.
Just forgot myself to